got an equilateral triangle of sides 2 centimeters and the point P lies on LM such that LP is X. So that's been labeled, and this would be 2 minus X, wouldn't it? This length here. I don't know if we'll need that, but I'll just add it on. And then similarly, Q is chosen such that this is Y, and therefore this length here is going to be 2 minus Y. And P and Q are chosen, so we're allowed to move them around, but it must be that the area of LPQ, that's here, is half the area of LMN. That's the bigger triangle. Note also, because it's equilateral, we can add on these angles, 60 degrees, 60 degrees, and 60 degrees. We're asked to show that xy is equal to 2. So I can say that the area of triangle P or LPQ, that's the same as PLQ, is equal to a half times the area of triangle LMN. And therefore, I can apply a half AB sine C. So for the smaller one, it's going to be a half XY sine 60 is going to be a half times a half times 2 times 2 times sine 60. So this part is the triangle, and this part is a triangle, and then I'm finding half of it. Now, this half will cancel with this 2, and this half will cancel with this 2, and this sine 60 will cancel with this sine 60, and I'm left with a half xy equals 1, from which it follows xy must equal 2. And we've done the first part of this question. In part B, we're asked to find the shortest possible length of PQ, justifying our answer. So that's going to be a calculus problem. What I'm going to do is I'm going to let PQ equal Z. Let's call it something. And now I can think about how I can get Z in terms of X and Y. I can use the cosine rule. It's got to be that Z squared is going to be X squared plus Y squared minus 2XY cos 60. Well, remember, we've just shown that xy is equal to 2 above, and we also have that cos 60 is equal to a half. So those are going to cancel, and we'll get z squared is going to be x squared plus y squared minus 2. That's not too bad. Right, but how do we maximize this? Well, we want to differentiate z with respect to either x or y. Now, I normally go for x because I'm just sort of used to doing that. Now, we can't do that yet because remember, y is a function of x, and so we need to replace it. We need to change it, and we can do that by, again, using xy is equal to 2. So it must be that y is equal to 2 divided by x. And therefore, z is going to be x squared plus y squared, which will be 4 over x squared minus 2. And I'll just leave that for a second. So it's actually z squared. What I can do now is I can square root. So it's going to be x squared plus 4x to the minus 2, if I get it in index form, minus 2. All of this is to the power of a half. I don't need to consider a negative because I'm talking about lengths here. And find dz by dx. So this is going to be the chain rule. I'm going to bring the half down. I'm just going to write this back in to fractional form. This is going to become minus a half, and then I'm going to times by the inside differentiated using the chain rule. So it's going to become 2x minus 8x to the minus 3. It looks messy, it is messy. This will equal 0 for stationary points. So therefore, I just want to kind of tidy this up a little bit. It's going to be um, 2x minus 8 over x cubed. I've just taken this part because it's sort of, this is on top. And I'm going to be dividing by the square root of x squared plus 4 over x squared minus 2. And I'm finding a half of it, so I can put a half here, and that is equal to 0. So one thing I can do straight away is I can cancel that half with that 2 and partially with the 8, 4. Now for this to equal 0, it must be that the numerator is 0. I can't divide by anything to get 0. So it must be that x minus 4 over x to the 3 is equal to 0, which means if I times through by x cubed, it must be that x to the 4 is equal to 4. This would give x squared is equal to 2 if I just take one square root, or x is equal to root 2. Again, I don't need to consider any negatives because this is a lengths problem. And therefore, y, because they multiply to give 2, y must also equal root 2. And z squared will therefore be x squared plus y squared minus 2 times x, y, whoops, x, y cos 60, which was a half. They're going to cancel. So I'm going to get 2 plus 2 minus 2. I'm going to get 2z. I mean, you might have sort of guessed it at this point. If x is root 2 and y is root 2, yes, it's going to be an equilateral triangle. Z is also equal to root 2. Cool. Quite a few little steps there to do. I don't think that's easy. Apply the cosine rule, make z the subject, differentiate, find this, consider that the top is just equal to 0 to get x, and from that get y, and hence z. Now, the only thing I've not done is actually, it did ask me to find the shortest length justifying my answer. Did that mean justify its a minimum? I feel like that's always implied in these sorts of questions. If I was doing this in a real thing, it might be something I come back to because, you've done most of the groundwork and this is just going to be to get like an extra mark or something. But let's have a look at it. I suppose intuitively might say yes, an equilateral triangle is going to work because otherwise, I can start drawing lines coming down. It's clearly going to be longer if I have, a more vertical line. So maybe I could justify it and say, for a given perimeter, or sorry, a given area, an equilateral triangle will minimize the perimeter. Maybe I could try and get away with that. Like I haven't proven that though. I suppose that's kind of what I'm being asked to prove, in fact. So I'm not sure that really counts. The way that I thought about it was to return to dy to dz by dx, in fact. We don't want to be taking the second derivative here. Like I think in theory you could do that, but there it is. It's pretty horrible. You're gonna have to use um, some serious calculus and stuff to get this. Okay, I can still cancel those out, so that's not a problem. And the way I'm going to show it now is what you have to do when the second derivative is 0. We know we have a stationary point. Okay, we know we have 0. We want to show that we have a minimum, and therefore we want to look at dy by dx either side. So we want to show that to the left we get dy by dx is negative, and to the right dy by dx is positive. But we don't have a calculator, that's one little issue. So I can say for x equals root 2 minus a small amount. Just going to do, like, say it like this. Well, this thing here is still going to, it's definitely going to be positive. Okay, this thing here is always going to be greater than 0 because I'm adding, well, for the values we're talking about anyway. I think probably for all values, in fact. I'm just gonna convince you of that actually, because I could write. I feel like this is going into more detail than needed, but I could write x squared plus 4 over x squared minus 2. I could factorize out a 1 over x squared, and then it'd be x to the 4 minus 2x squared. I'd have to times that by x squared plus 4. And now I could actually sort of complete the square, but in terms of x squared, it would be x squared minus 1 squared. That will give me x to the 4 minus 2x squared. And then I need to minus 1 and plus 4. I'd get this. And you can see that this is always going to be greater than 0 because x, this is positive, this is positive. So actually, I think the minimum value would be 3, in fact. So I've convinced myself that this must always be positive. And that just means I need to look at x minus 4 over x cubed, which I could write, I could factorize the x out and have 1 minus 4 over x to the 4. And for x is root 2, a little bit smaller than root 2. Like when I make this small, so when it's equal to root 2, this thing is 0. But when I suddenly make it less than, like if I made it like 0.1, for example, then this term is going to be massive, and this is going to become negative. So I'm trying to convince you basically that this thing here will be less than 0. And therefore dz by dx will be less than 0, which is what we wanted. And meanwhile, for x equals root 2 plus a small amount, x minus 4 over x cubed. If this is big, like if this was 100, for example, then it's clearly positive. And as soon as it goes above root 2, it's also going to be positive. Hence, x equals root 2 and z equals root 2 is, remember this is PQ, is a minimum. Okay, I feel personally that that is definitely, more than enough justification. One more part to go. Now, I think this is the hardest question in the paper to like fully understand. I had to read it several times to even like figure out what it's talking about. Mathematicians know that for any closed curve or polygon, enclosing a fixed area, the ratio area enclosed divided by perimeter is a maximum when the closed curve is a circle. By considering 6 copies of triangle LMN suitably arranged, find the length of the shortest line or curve that can be drawn from a point on LM to a point of LN to divide the area of triangle LMN in half. Justify your answer. So what this is sort of saying is, right, we don't have to just use a straight line now to go from P to Q. We could do some sort of curve, and essentially what would the length of that curve be to be able to um, minimize it essentially. Sorry, how would you minimize? That's it. How would you minimize that length PQ if it doesn't have to be a straight line? I kind of just modeled my way through this one and somehow got the right answer. And I'm just gonna say, like, I'm just gonna kind of guide you through what I did. Like, I kind of thought, right, the hint really is considering 6 copies of triangle LMN. So how are we going to use these 6? Well, it kind of makes sense, and it's helpful to know this, that you can use 6 equilateral triangles to create a hexagon, a regular hexagon. So that is a little sketch of my regular hexagon. Now I'm going to focus on this triangle on the right, and I'm going to, maybe this is P here, and this is Q. Now what the top statement is sort of saying, I think, is that basically we can draw a circle like this. And this links in. Mathematicians know that for any closed curve or polygon enclosing a fixed area, so I have a fixed area here. I know I've only got half. Yeah, we've already gone with using a straight line. And when I was using a straight line, I'd have to move P and Q and it would be over here somewhere. Like I'd get a polygon if I moved it all the way around. But if I want to maximize the area enclosed by the perimeter, then I need to use a circle. And what in sense that is saying is, right, we actually have a fixed area here. Okay, it's half of the area of this triangle. But I'm talking about this area here that we're trying to create that is half of the big triangle. Now that is a maximum when the closed curve is a circle, and the consequence is that it must be that the perimeter is a minimum because the area is fixed in our case. And if the perimeter is a minimum, that means that this portion here, P to Q, this length must also be a minimum. Therefore, a an arc minimizes um, length PQ. Now, I just want to remind you, if you do a straight, that's not quite, is it? Minimizes the, it's not minimizes length PQ, it would be a straight line that would minimize length PQ. It's that it minimizes, that we can basically move P and Q closer to one another to give this half area. So an arc is the shortest, I just want to get my wording right. An arc is the shortest line that divides area of triangle LMN in half. Okay, that's better. And my circle will have radius r. And remember, we know, so the area of triangle LMN, remember um, it was a half times 2 times 2 times sine 60. Just trying to remember, they cancelled. So that was root 3 over 2, so it gave me root 3. Therefore, half of this equals root 3 over 2. And therefore, pi r squared, that's the area of the circle, is going to equal 6 lots of this. Because I've got the whole circle, and I need to basically add up all little 6 segments that I've just found. Or equivalently, I could, if you prefer, you could say, right, I need to find a sixth of the area of the circle and set it equal to that area of the triangle. If you want to think about it that way, then that's okay. So that's going to mean that r squared is equal to 3 root 3. Sorry, pi r squared is going to equal 3 root 3 if I times through by 6. And so r squared is going to be 3 root 3 over pi. And therefore, I think that's okay. So r is going to equal the square root of 3 root 3 over pi. Let's leave that for the moment. Therefore, minimum length is going to equal 2 pi r over 6, because it's my circumference divided by 6. Which is pi r over 3. Which will then be pi times 3 root 3 over pi all over 3. This doesn't look nice, does it? Let's be honest. But we can simplify it. We can write it as pi times root 3 times root 3. I'm going to leave it like that for the moment. Then I'm dividing by root pi. And I'm just going to change that 3 to root 3, because then I can cancel this, cancel this. I could even change pi to root pi times root pi and cancel these out. And overall, I'm going to be left with root 3 pi over 3 all square rooted. Which, actually, sorry, I could write as pi over root 3 all square rooted. That is our minimum length that would divide that triangle into 2. I found it quite hard explaining this actually. I sort of just kind of did it and it happened to be right, and I haven't completely got my head around it, I don't think. I've tried to convince you along the way. We're using the fact that the arc is the shortest length that divides the area of triangle LMN in half because of this statement here. So I've then used the area of the triangle, divided it by 2 to give me the area that I actually want. We've enclosed the circle, so this red area is what we want to find, and that's what we want to set equal to that half of the triangle area, which is what we did here basically. Either 6 of the triangles is equal to pi squared, or 1/6. So this sector area is equal to root 3 over 2. Solve to get r squared, and hence r, and hence find out this arc length, which is the minimum length that you can possibly get to split the triangle into 2. The only thing to say right at the end is that it does ask to justify our answer, and have I done that? I probably need some words. So I'm just going to write, like at this point, I'm going to write kind of what the mark scheme has said. I feel like I've sort of said this, but since circle is best curve for half area, that's using what I said above, the fact that you know, it's maximizes the area divided by the perimeter. That's what we were told. Um, Actually, since it half area of hexagon, which is obviously linked to the triangle by symmetry, the circular arc must be best for LMN. I kind of feel like that's what I did already over here. So maybe this is really linking in, you know. Um, I've kind of said it up here already, but this is what the mark scheme said, so I thought I'd add that at the end. I personally think I've done that, but I'm going to stop talking about this question now. That's a hard question. I hope I've made it a little bit clearer if you didn't know at all what to do. Um, and yeah, well done on your efforts on this last part.